Classifying PDEs. PDEs often have an infinite number of solutions. However, when applying them to physical systems, we usually assume there's a deterministic, or at least a probabilistic, sequence of events that will occur. Therefore, we impose additional constraints on a PDE, usually in the form of initial conditions, which are values of independent variables over all space at an initial time, and boundary conditions, values of independent variables or their derivatives over all time. Ideally, imposing such conditions leaves us with a well-posed problem, which has three aspects. Existence, so there exists at least one solution. Uniqueness, there exists at most one solution. And stability, if the PDE boundary conditions or initial conditions are changed slightly, the solution changes only slightly. Okay? So if that wasn't the case, then we would have a problem that is not well posed, okay, if these are not the case. As with ODEs, PDEs can be linear or nonlinear. That is, the independent variables and their derivatives can appear in only linear combinations, linear PDE, or in one or more nonlinear combination, nonlinear PDE. As with ODEs, there are more known analytic solutions to linear PDEs than nonlinear PDEs. The order of a PDE is the order of its highest partial derivative. A great many physical models can be described by second-order PDEs or systems thereof. Let U be an independent scalar variable, a function of M, temporal and spatial variables, xi. A second-order linear PDE has the form, for coefficients alpha, beta, gamma, delta, real functions of xi, equation 7.1. So let's inspect this term by term. So we have this first double sum that has second partial derivatives of U, the independent scalar variable. Second partial derivatives with respect to the different variables. So this could be like one spatial coordinate and then another spatial coordinate. It's like x, y, could be x, x. So it could be the second partial with respect to x, could be partial with respect to y, partial with respect to y, so the second derivative with respect to y. And then corresponding coefficients. The coefficients can have in them, they can be functions of those independent variables, like space variables, for instance, like x, so the xi's and xj's in this case. Okay. It could also, these xi's and xj's could be time. Okay, time could be one of those. All right. And then there's another term here where we've got the first partial derivatives of U with respect to each of the independent variables, xk, and corresponding coefficients of those, which can also depend on x. And then the zeroth partial derivative, so the just linear, or the linear term, so delta k multiplying U. So there's no derivative in that term. That delta is just a coefficient there. So there's a sum of those. And then on the other side, there's the forcing function. Okay. Where f is called the forcing function, f being the forcing function. And it can be a function of the x variables, the independent variables. When f is 0, the equation is called homogeneous. We can consider the coefficients alpha ij to be components of a matrix A with rows indexed by I and columns indexed by j. There are four prominent classes defined by the eigenvalues of A. Elliptic. In the elliptic case, the eigenvalues all have the same sign. Okay, so we all know how to find eigenvalues. So Find the eigenvalues of that A matrix, and if they're all negative or all positive, then it's an elliptic equation. Parabolic. So the eigenvalues have the same sign except one that is 0. Okay, so they're all negative and 1, 0, or they're all positive and 1, 0. The third one, hyperbolic. Exactly one eigenvalue has the opposite sign of the others. And finally, ultra hyperbolic, which is very rare, at least 2 eigenvalues of each sign. So this is a case that doesn't show up a lot in physics, but it is mathematically a thing that's well defined. The first 3 of these have received extensive treatment. They are named after conic sections due to the similarity the equations have with polynomials when derivatives are considered analogous to powers of polynomial variables. For instance, here's a case of each of the first 3 classes. So the second, I should have a squared here, shouldn't I? Second partial of u with respect to x, and then there should be squareds on these too. Not on the last one though. So second partial of u with respect to x plus second partial of u with respect to y equals 0. That is elliptic. Notice that the equation for an ellipse, well, the equation for one type of ellipse is x squared plus y squared equals 0, right? That's an equation for, it's just a circle. Or not, I guess not 0, that would be 0 radius, but we would put a number there. But it has that form of something squared plus something squared equals. And then the hyperbolic one has a similar form, except there's a negative sign that shows up. And that is the equation. It would be x squared minus y squared equals something. And that would be a hyperbolic algebraic equation. And then we call this parabolic when you have one that's of a lower order. So one of them disappeared, like the dxy, or the dyyy disappeared, for instance. So this is a parabolic equation. This is a common one that we'll see later, actually. When a depends on xi, remember in general, those alpha coefficients can depend on the independent variables xi. It may have multiple classes across its domain. So the eigenvalues might have, they might all be negative for a while, but then in some part of the domain, one of them is positive. And so it goes from being elliptic to being hyperbolic. In general, this equation and its associated initial and boundary conditions do not comprise a well-posed problem. However, several special cases have been shown to be well-posed. Thus far, the most general statement of existence and uniqueness is the Cauchy-Kowalewski theorem for Cauchy problems. And these, so unlike when we had our theory of actually nth order linear ordinary differential equations, we had the existence and uniqueness theorem, right? And we knew that there was a unique solution if we had an initial condition, and given certain properties, we knew that it had to exist. In the case of general second order linear PDEs, that's not the case. Even with boundary conditions and initial conditions, it's not the case. So what we'll end up doing next lecture is we'll look at Sturm-Liouville problems, and those problems arise quite a bit and have a guaranteed existence uniqueness to them. So we'll look at those for boundary value problems, and then we'll learn the method of separation of variables, which will include the boundary value problem as part of it. And we'll be able to solve a pretty decent sized class of PDEs that show up a lot in engineering. So that's our goal. That's where we're headed. So, any questions on classifying PDEs? Okay.